My name is Henrik. I'm Henrik Drake. I'm a professor in environmental science at the Linnaeus University in Sweden. And I will talk today about deep microbial colonization during impact-generated hydrothermal circulation of impact structure. And I have some co-authors on a paper. This is basically showing a paper that we did with Jakob Gustafsson and Gordon Osinski, Nick Roberts, Jay Quaid, Shannon Wang, Martin Whitehouse, Heijin Jian, Andreas Karlsson, and Sato Hitala from various parts of the world. And I will go through that a bit later. But first, impact craters are cool environments and have been in many Hollywood movies, for instance, the Armageddon and Deep Impact. And there they say that this is like a catastrophe event. It destroys life, but to me and to others, it's also where maybe prebiotic reactions starts and where dead planets might come to life and where microbes might colonize or recolonize. So that's why I think it's a very interesting environment to look into, because it can be the onset of life actually, and not just destruction. So there are different sizes of impact craters, and these are different energies. So this is just a plot showing that the interval, or how often that these impacts occur. Like the Chicxulub in Mexico is a very rare and very high energy event, and then the smaller impact craters are more common because they are more likely to happen. And the impact crater events can be the onset of life, as I said. If we have a habitable world, we can have this prebiotic synthesis, and this can be sparked by the impact itself. We actually don't know how life started on Earth, so this is one of the hypotheses. And then it can go to further steps, polymers, and then protocells, and then maybe out into the Luca, the last universal common ancestor of eukaryotes, bacteria, and archaea, and then we might have it bloomed from there. So this means that it's interesting to look into ancient impact events, like around when life started on Earth. The earliest life on Earth is like 3.8 to 3.5, depends on the level of evidence, and it depends on it also comes from different cratons or different continents on Earth, like Australia, South Africa, and Greenland and Canada. So these are some fluid inclusions that show that it has been probably microbial methane, because isotope signatures in fluid inclusions show those type of values. And that goes back to 3.8 or something. And what you can see on this graph is that at the same time, it's a bit further back in time, there was the end of the late heavy bombardment on Earth and on the moon. And since we have had plate tectonics and we have had very diverse and dynamic surface environment, a lot of these signs of ancient life on Earth are gone and down into the mantle. And comparing them to moon can be an interesting analog, because most of it is still preserved, and there we can see this heavy bombardment being clustering early in the history. And we would suggest, or we would think, that Earth has similar amounts of impact events, or even more, because it has higher density and more gravity, higher gravity than the moon. So these times are interesting to look into, but there is no rock record, so we need to look into other impact craters on Earth, and they are younger, and the younger they are, the better preserved they are. So they are therefore of interest to look into certain biosignatures in those impact rocks. So this is what we have done here. So on Earth, there are more than 200 known impact craters in the rock record, and there will be more and more that are found every year almost. So this record is constantly increasing, but there is a lot already known, and the impact of the impacts itself is kind of interesting because it's like a hotspot where heat is increased, fracturing is increased. The heat is of course increased to temperatures that is too high for life, but it also sparks energy and gives rise to some specific environments that can be interesting for the onset of life. So this could be, according to a paper by Charles Coquelle that I took some parts from, some interesting features of the impact itself is that it provides the source of energy of and maybe even precursors that it might deliver organic precursors for the origin of life. It also provides energy and starts a hydrothermal system, which we call IGH, impact generated hydrothermal system, and then it might provide conditions in that system for synthesis of diverse organic compounds. It also mobilizes minerals. Some minerals are particularly interesting, but because it catalyzes electron transfer reactions and organic complexification. It also gives appropriate minerals for prebiotic reactions, like clays and zeolites are formed, and these are good because they have ordered surfaces and charged surfaces that can be sorption sites and for oligomerization of reactants, and it might be potential templates for prebiotic reactions, such as eelite and montmorillonite could be of interest for that reason. So it also gives these available surfaces. Other interesting features are that we have fracturing, melting, redistribution of target rocks, and we can have the geochemical gradients throughout that shifts throughout the crater itself, gives different physical-chemical conditions. It is also that different pH are more or less suitable for surface binding of organics. So non-acidic pH is the best to preserve organic material for that prebiotic sequence. There can also be establishment of thermal gradients within the crater. So this gives rise to zonation in secondary minerals, and also that we have this heat that gives gradients that drives the hydrothermal system. Then there is also a cooling effect, or there is the long-term cooling conditions is of interest, and a large impact structure will give much longer hydrothermal systems, so it takes longer for it to cool, and this gives time for complex molecules to form as we get to colder temperatures, which favor their stability. So we need to have necessary time for synthesis, not too long, but also not too short. So these are like the end members of this, and then we can have microbial colonization as well in these different environments. So this could be a safe haven for microbes to escape to. It could also be that microbes, or that they start their life in these type of systems. But they have some kind of hotspot systems, we can call them, because they are perfect to colonize. They are fractured. They are also high porosity rocks, and there are glasses. So these different environments give rise to different habitats, so let's say sub-habitats that could be colonized. There are some examples that I will show of colonization of impact glass. There are endoliths that colonize shocked rocks. There are hydrothermal veins that also have biosignatures that we could be interested in. And then there is the crater lake with subaqueous hydrothermal vents and subaerial hydrothermal vents on next to the crater. So an event sequence would be that we have a first thermobaric phase that is very close to the formation of the impact. When the impact event happened, we get fractured rock, we get porous rocks and glasses at this time. Then temperature and pressure decrease, and then we get the hydrothermal phase, where we get crater lakes, hydrothermal systems in the vesicles and in the veins. And after that, we get a long post-impact succession phase, where we start to weather and we start to erode the crater, and we get sediments in the crater lake and so on. So these are interesting phases, and we would like to, as close in time to the impact, see when life colonizes this environment. So the time it takes for impact structures to cool down has been estimated for several craters, and the larger ones take millions of years. And then it's also a matter of what is the temperature we are talking about. And many of these models, they are ending at temperatures that are quite high, that are 200 degrees or something. And I mean, microbes can colonize, and they are actually thriving at 40 degrees, most of them, or around 37. So that is, the models are not fully showing the whole elevated temperature length of an impact system. The smaller impact crater or mid-size impact craters, Horton, Rees, and Lappajärvi, they have been shown to have very different lengths of this system cooling. Especially Lappajärvi is very long term, and I will talk more about this in this talk. So biosignatures on Earth today are not so commonly reported in impact craters. There are, I think, maybe 8 studies showing them, or maybe 9 or so now. And they are different biosignatures for different craters. In Chicxulub, Kring et al. Showed sulfur isotope evidence for sulfate reduction. In Chesapeake Bay, there have been some trace fossils shown. In Horton, Parnell showed also sulfur isotopes. In Rochechouart, Simpson et al. Showed also sulfur isotope values for sulfate reduction. In Rees, Sapers, and also other studies of the crater lake has shown these Sapers showed impact glass with filaments in it. And in Siljan, Hude et al. Showed some microbial mats or microbial EPS structures. Lindgren in Delland showed these body fossils or fossilized fungi or filaments in glass. And myself and Mikael Tillberg have shown isotopic evidences and filaments in Siljan and Lockne in Sweden. So if we go into chemistry or the isotopic chemistry to distinguish different processes of like microbial sulfate reduction, we can use the very well-known fractionation that is different between when it's microbial and when it's abiotic. So when we have sulfate reduction, we can have both precipitation of very negative sulfur isotopes in pyrite and also negative carbon isotopes in calcite from this process. When we talk about methanogenesis, because methanogens prefer the lighter carbon over the heavier, we have a 13C enriched residual CO2, and then calcite forms from that will be then positive in carbon isotopes. And anaerobic oxidation of methane is a third process that is using the methane and inheriting that very light isotope composition of the methane, whereas sulfate is also then reduced in a coupled process if it is sulfate dependent anaerobic oxidation of methane. Then we get low values in carbon isotopes, and we get low values in the beginning, at least, in pyrite. So we can use this, and if we have that in mind, we can go to the Siljan ring or the Siljan impact structure in Sweden, where there are some ongoing gas prospecting campaigns that have been doing drilling of drill cores that we have been using. It's also an astrobiological analog, like all impact craters. So it's a proterozoic rock, host rock, and then it's a ring of downfaulted Silurian and Ordovician rocks. And one of the earlier studies was in 2005, where Hude looked at hydrothermal veins in the Ordovician limestones and found some interesting filaments, but provided no more context really than the filaments being there themselves. And this is tricky because who knows if they are actually more modern than the impact event itself, because there was no geochronology evidence to it. So what we did in 2019 was to look for evidence and try to date isotopic evidence of biosignatures. And we could find very heavy carbon-13 enriched biosignatures in some calcite fractures in the impact in the upper sediments. We could also find it at great depth in the crystalline host rock and the target rocks in these breccia systems, and we could find biomarkers as well for different microbial species, anti-ISO C17, for instance. So those are of interest because they might be sulfate reducers. And at the boundary between sedimentary rock and crystalline rock, we found very light values that suggest anaerobic oxidation of methane. And when we dated them, we got ages that are very much younger than the impact. Impact is around 380 or 378 or something. So these are like 300 million years younger. So therefore we could say that these are definitely not impact related, but it shows that the system has been very prone to later microbial colonization. We also found some interesting fungi that are growing in some vesicles, and they are related to calcite that have methanogen signature, but these are basically 39 million years old at most, so they are also unrelated to the impact structure. But shows that just because you find biosignatures in an impact crater doesn't mean that everything is related to the impact itself. So it's very important to get the full context also of geochronology evidence. We did another study in Lockne impact crater, which is 458 million years, and there Magnus Ivarsson had previously found fungi that also then were interpreted as impact related, but our dating showed 100 million year old younger, to be 100 million year younger than the impact event, which also disqualified that evidence. So comparing then Lockne here, Siljan here, all the biosignatures in yellow, and some filaments here, and live methanogens that we have found in a separate study, they are all younger than the impact event. So these tubes or filaments that have been found in previous studies also probably are not impact related, but it remains to be like evidenced. Moving to Dellen, which is a younger impact crater, like half the age or a bit younger than that, 140 something million years. There's a Dellenite impact rock, which is specific for Dellen. And there are studies of hydrothermal systems that have some fractures in this impact structure with some interesting filaments that have been taken as impact related microbial colonization. But there is still no temperature estimate and no age proof for this. So it remains to be understood what actually they are and what happened and at which time it happened. Some other structures are the Horton structure, where Pernell published a story about sulfur isotope signatures for rapid colonization by thermophilic microbes. So this is also, the title itself tells us that it's very quick and it's very hot for these microbes, and they provide very nice sulfur isotope values, which are down to -25 or so, and that is much lighter than the anticipated initial sulfate, which is around 25 or so. So that is perfect, above perfect biosignature. Even marcasite is even lighter, but the age of these mineral precipitations are actually not known, and there is no temperature, so we cannot really say that it's a rapid and thermophilic event, but definitely biosignatures. Same for Chicxulub. Kring et al. Showed very nice pyrite observations and calcite observations in a nice paper, and they also made a good job, or made a solid job, to get the initial sulfate anticipated from anhydrite in the crater in the target anhydrite in the crater, and then compare it with sulfides that go down to -35 or something. So definitely microbial pyrites in this case. But also here, no age actually reported. There are petrographic evidence. So still it suggests that it's impact related, but we don't know when in the process or at what temperature, or if they actually are younger than the impact event. In Rees, there are these tubes that Sapers provided also there. They're likely microbial, but still they don't have any timing or any temperatures for it. There are some crater lake studies as well from Rees that you can look into if you wish, that shows some carbon-13 enriched dolomite, for instance, that are strong support for methanogenesis in the crater lake. But I won't go into the crater lake environment. I will stay in the deep subsurface, and I will talk more on the Lappajärvi impact crater now, because it has such a long time of cooling. So we thought this was a good target to look into and see if we can pinpoint microbial colonization of an impact structure. So this impact structure has a record previously published where it forms here, and then there are different proxies for temperatures by different minerals, and that goes then to show that it's about 1.3 million years to get to this stage at 240 degrees. So it takes a long time to get down to 240 degrees, and microbes, they live at 120. So it might be that we could get further into the system in time and get microbial colonization much later than 1.3 million years. So this is definitely a very long-term cooling event. So Lappajärvi is in Finland. A lot of impact craters are in Finland, and we are then talking about this crater here formed at 78 million years ago. So we published a paper that was led by Jakob and us about this deep microbial colonization of the Lappajärvi structure. We focused on impactites, impact melt rock, which is called kernite in this area, impact melt-bearing breccia, so-called suevite. At different places on Earth we have seen the same, but it's called impact melt-bearing breccia commonly, and then also lithic impact breccia, which is more of the target rock involved. So the target rocks are metagraywacke, mica schist, mica gneiss, and pegmatite. And there are two boreholes that we focus on. One has this melt rock kernite in the major part, and then suevite at depth, and the other has suevite. So we sample these parts of the impact crater for veins and vugs that are partly filled with calcite and pyrite. Also in the suevite, we focused on these kind of vugs and partly sealed or completely sealed vugs and vesicles. So what we wanted to do is to detect signs of ancient microbial processes, determine timing of colonization, and detect remnants of a low temperature hydrothermal system, and at what temperature. So we use the toolbox of optical microscopy, we use scanning electron microscopy, and then we use secondary ion mass spectrometry, which is our main method to find out about the isotopic composition in microscale. Then we use clumped isotope for the temperature of calcite, and then we use radiometric dating together with BGS, laser ablation, ICP-MS, for detecting the age of the calcite, and then organic geochemistry, if they are not too contaminated, to find out about organic molecules preserved. So Lappajärvi has this kernite, which can be divided into several sections, vugs with calcite and pyrite at different parts of the rock. And the upper part and the lower part have more vesicles and veins, so we focused on those parts. The suevite we took at several different depths, and especially where we could see pyrite and calcite in the vugs. We tried to find also these kind of glass, melt glass with pyrites, and we tried to look into vugs that looked like completely sealed off. So we hoped that the biosignatures would have formed at the impact event and then would not have been disturbed or no later colonization. And some other bugs as well, bigger bugs, with altered glass around it. So they are nice. The isotope signatures that we found, specifically we found sulfur isotope evidence of bacterial or microbial sulfate reduction, very light isotope values in the interior part of the crystals, and then as we go further out to the rims of the crystals, they get heavier. And this is due to microbial fractionation and then Rayleigh distillation, which gives a heavier pyrite with time, because the sulfate pool is being exhausted by precipitation and sulfate reduction. So this is solid evidence for microbial sulfate reduction. The calcites showed several groups of values. Some of them in the impact melt-bearing brachia, they are light, down to -30 or so. So we interpret them as organotrophic. And then there is these really light ones that we think are anaerobic oxidation of methane, going down to more than -50 per mil ppb. In the impact melt rock, we have three groups. One that is heavy in oxygen isotopes and quite heavy in carbon. The other are also heavy in carbon, but lighter in oxygen. One of them is really heavy in carbon, like carbon-13 rich, up to 20 per mil almost. And that is something we think definitely is methanogenic and formed by methanogenesis. So we can detect ancient microbial processes for sure. So can we detect the timing of the colonization? Then we looked into the different groups and tried to pinpoint the same groups that we have in the sulfur, in the carbon isotopes, with uranium lead dating in situ in the same spots. And then we got values or ages that were quite young, 43 point ±9. This is a kind of uncertain age. It's not the best, probably because it has formed over a long time and then given a mixed value. So around 40, 50, somewhere there for that one. The outermost part, AOM part, we could not date really nicely. We got a very huge error, but so we cannot say if it's impact related or not. But since the core of the crystal is 43, we can definitely say the outermost part that is formed later is not impact related either. The other groups are, the second group here is 62.5 ±3. So also not impact related, but this first one is coming closer to the impact event itself, and basically within error of that late stage impact event, impact generated hydrothermal system cooling. So we could actually, in one of the groups, say this one is the oldest one, and it looks like it's related to the impact event. And looking in details of this group, it sits on the edges of these veins and has pyrite, and the pyrite is actually the one with very light values of sulfate reduction, so we can tie the age to sulfate reduction or tie sulfate reduction to that age, whereas the interior of the veins, they are the lighter calcite group. It shows that these veins have been reactivated at a later stage, 10 million or 15 million years after the impact. So just getting biosignatures doesn't tell you that you actually have impact-related colonization. So it's very tricky, and only these tiny outermost part, or these rims of the vein here, are impact-related in this case. So just a couple of paragenetic sequences, how we determined also the different spots, where we put the different spots, but won't go into detail. But we used this technique, or we use this very detailed paragenetic and petrographic evidence also for our determination of the low temperature hydrothermal system in temperature. When we had determined the timing of colonization, we went to clumped isotopes to get the temperature of colonization. And this is the first group at 74 million years at 47 degrees and around 40, somewhere there. The later part, 63 million years, they are at 30, and then the later ones I have the same crystals here showing that. So the first part is in the melt rock, and then the later stages are in the swayite. And they are late and they are low temperature. So there is a sequence of colonization. So this slow cooling gives us the calcite ages here on the temperature. So these were the previous ages and temperatures by the thermal chronology studies, and we are now here. So it fits to this very late stage cooling model. So we have a sequence of events. The colonization starts in the late stage hydrothermal events. After we have formed the veins, we have them on the fracture walls, and then we fill it up with later calcites, whereas the vugs in the swayite are filled at the later stage. And it also fits to Fennoscandian shield model of how the crust has been going up and down, being habitable at the green events, and Lappajärvi is somewhere here, and after that it goes only towards lower temperatures, so it shows that we have not had a reheating of the area, which shows also that these high temperatures have not been occurring later than the impact. So we can mark all these different parts. And then discussing why it might be that this system is so long-lived in Lappajärvi is of interest. But it could also be that these other are much more long-lived than the models show, because we are talking about 47 degrees here, which is usually not involved in the models of hydrothermal systems. So it might be that we need to rethink the models of cooling of impact events, and that colonization might be much later, but in the cooling phase itself. That could have also astrobiological implications of how to think about hydrothermal systems in impact craters. So the main potential heat source that drive these systems are impact melt rocks and impact melt bearing breccias. If we have them, we have also elevated geothermal gradients in central uplift. This could also be a reason why we have elevated temperatures for long times in Lappajärvi, and it can be energy deposited in the central uplift due to passage of the shock wave. And Schmieder and Jordan also put forward a couple of these different ideas of why we have this long cooling period in Lappajärvi. And one of them is an elevated geothermal gradient due to the impact-induced uplift, and that we also have residual heat generated by shock and friction within the central uplift. Also that we have a crystalline rock that is very dry, and that the crystallization heat released during hydrothermal alteration may play a role. There is very low permeability of the target rock, and it could also be that we have cave feldspars that insulates. So definitely there is a difference between, for instance, reese, which is in a sedimentary target, and crystalline targets. So it might be then that crystalline targets are of interest to for if we need long time for life to evolve, then it looks like crystalline rock targets are more interesting because they have such a long-term cooling of the hydrothermal impacts systems, and it could be due to the rock itself. Because in sedimentary rocks, they have water and other volatiles, and the impact causes them to flash vaporize, and this leads to rapid quenching, and then the expansion of the volatiles disperses the impact melt quickly and break it into smaller fragments to this really porous swayite that cools really fast. So this volatile-rich environment promotes active fluid circulation, removes the heat very rapidly, and there's also very high porosity. In crystalline targets that are really dry and dense, like gneiss and granite, like the one we have in Lappajärvi dominated basement, it has much higher melt volume. So less energy is used for vaporizing volatiles, and more energy is then put into the melting. And it's much a slower cooling because these rocks are very large, form very large melt sheets. And this is what we see in the Cairnite. And in the Cairnite is where we find also these biosignatures that are formed quite late, but still at elevated temperatures. So we would then suggest that impact melt rocks and impact melt breccias are the main heat source here that provides heat for a long time. So we have detected in this study the first coupled isotopic temperature geochronology support for microbial colonization. And in this case, it's microbial sulfate reduction that is with the pyrites that we find. And then we could then date and get temperatures from cogenetic calcites. And this also supports previous claims that circulation at this impact generated hydrothermal circulation can be sustained for a very long time at this impact crater and at other impact events as well, perhaps, especially when they are in the right rock type. We also show methanogenesis and anaerobic oxidation of methane. There is solid evidence for those as well isotopically, but they are much later formed. So we could prove that, and then we could reject that theory that we have formed also, that we also have methanogenesis and methane oxidation at the impact event. And it's basically an analog for the emergence of life on Earth and possibly Mars, because it shows that impact events can also involve microbial colonization, and that the impact events, they can also be preserved as biosignatures, or the colonization can be preserved as biosignatures. So future prospects, we have done Lappajärvi now, but there are 200 impact craters still to investigate. So we are on it, and it would be cool to see more research done on this topic, because we know so much about the impact events. We know a lot about models for how they formed, at what angle they came, what target rocks they are, what type of impactor, and what time it happened. But we also have modeled a lot of hydrothermal systems. So there are a lot of hydrothermal system modelers that also are looking into Mars and doing models on Earth for terrestrial impact craters. But there's very little attention paid to the post-impact features, the low temperature evolution. And this is a bit of a pity, because the motivation for studying the hydrothermal models are that the impact craters are good environments for colonization and perhaps for an onset of prebiotic reactions. So there's also very little done on molecular biosignatures and on microfossils that are very close in time with impact, and also we are lacking that higher temperature hydrothermal colonization. We are at 45 degrees, 50 degrees, somewhere there, but we haven't found biosignatures that are definitely higher temperature than that. So we are now also focusing on other impact craters. So Jakob and Gordon Osinski and myself, we have been taking a lot of samples. So we have many studies that are in the pipeline. So we're looking forward to have some more evidence coming out in the coming years. Some astrobiology implications of these studies are definitely that these type of systems are, for me, a nice focus. We should, in my view, focus on them when looking at other planets such as Mars. I mean, it's very easy to say, but it's very difficult to drill deep. But if possible, I would suggest to drill into these kind of rims of impact craters where there are a lot of fractures, because we show that it's a good potential for colonization. It's a good potential for preserving biosignatures over geological time. And it could be that these biosignatures and even microbial life could have escaped down there and survived radiation and oxidation. So biosignatures can be preserved, perhaps even organic biosignatures. So optimal targets would be to go deeper and go into impact-related fractures and bugs and look for isotopic signatures and try to find that. So there are some studies from Mars that are also showing these type of methane and sulfur isotopes that are definitely intriguing to look more into, and also studies showing that Martian impact fracturing influences habitability under. So impact craters are definitely something that is of interest. So thank you for your attention.